Hi everybody, Physics Ninja. Today we're going to look at the vertical simple harmonic oscillator. Okay, this is to continue a previous lecture I recently did on the horizontal spring and mass system. Today I want to flip it in the vertical direction. What we're going to do is I'm also going to use some PhET simulations to kind of look at a couple test cases. The first thing we're going to do is find the equilibrium position. That is the most important difference between the vertical and the horizontal mass spring system, right? Because when I hang a mass on the spring, it's going to go a little bit lower. We need to find that starting point, that equilibrium position before we do anything else in this analysis. Now, the second part we're going to do is we're going to use Newton's second law to look at the equation of motion. And we're going to find that it's the exact same as the horizontal case, except that it starts at a different position. Okay, the equilibrium position is different. And in the last part of the video, I also want to look at energy solving problems using energy methods. How do you write the total potential energy of a system when it's in the vertical orientation, right? What is different and what is similar to the horizontal case? All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, we've got our vertical spring, and the vertical spring has a length L0, which I call the natural length of the spring, and it's going to be characterized with some spring constant that I'm writing as K. That tells you how stiff the spring is. Now, when I attach a mass M to it, it's going to stretch a little bit. I've called the amount of stretching Y0. Now, let's recall from the class, Hooke's law is a force from the spring is typically written as something like this, minus kx. K is the spring constant. Negative tells you the direction of that force, and x is how much it's stretched. So we're going to have to apply it to this second picture right here. What I want to do is draw a free body diagram on that mass M. First of all, there's the weight acting down. That has a magnitude mg. Now, how do I write the force of the spring? Well, the direction you should know. The direction has to be straight up. Now, how would I write the magnitude of that applied to this spring right here? Well, I would simply write it as Fs is equal to, forget about the negative sign, that just tells me the direction, but you know it has to be up. So it's the spring constant K. And now if I use this stretch distance Y0, I would write it as something like this. Okay, now if it's in equilibrium, guess what? Both of these forces have to be the same. So you have to have that Ky0 must be equal to the weight of the object. So right away, if you're given the spring constant, or if you don't know, if you measure in the distance that it's stretched, you can determine the spring constant, right? If I just work with this equation right here. So there's kind of two things I could determine, right? If I wanted to know the spring constant, I just bring the amount of stretch on the other side, and it's Y0, right? That could be an equation I could use to determine the spring constant. The other one is if I know the spring constant, I can tell you exactly how much it's going to stretch, right? It's going to stretch this much. And you can see that the bigger I make K right here, the less it's going to stretch because it's going to mean a stiffer spring. All right, so let's go to the PhET simulations, and we're going to model this and to see how we can use this equation to calculate these properties. All right, the first thing I want to do is using our PhET simulation, what I did is I suspended a mass here, which was equal to 100 grams. So that's 0.1 kilograms. In this first case, you notice that it stretched a little bit, right? This was our distance here, Y0. So my goal now is to determine what is the spring constant K. I can use this first equation that we had, simply equal to the weight. So I have 0.1, what else, times 9.8, and divided by what is the amount of stretch distance. So I have to measure this. Well, the equilibrium position is right here, right? This is sort of the unstretched spring. That had a length of 0.48, right, 48 centimeters. 0.48 meters, and this last one down here, it's approximately 64. Yeah, let's just say it's roughly 64. So 0.64 meters. So guess what? That means that my Y0 distance, Y0 is only the amount that it's stretched. So you have to take the difference between both of those. Minus 0.48. So then you get 0.48 16 meters, right? 16 centimeters is how much I stretched it. So I can go ahead and put that over here, 16. And now you just tabulate that, and you're going to get a spring constant, which is equal to 6.125, and that should be measured in newtons per meter. All right, so that's how you can find the spring constant. The next thing we could do is, well, what if I change the mass? What if instead of 100 grams, what if I grab one of these bigger ones and I hang it on the same spring? What do you think is going to happen? Well, it's going to stretch a lot more, right? So we can then calculate how much is it going to stretch if I place this one instead of the 100 grams. All right, so let's go ahead and do that. Let's do the experiment using the PhET simulation. I did that on this page here. So I hung a mass of 240 grams. And let's see what the Y0 is now. So again, I started at approximately 48 here. Then I'm going all the way down here. I'm going to about 88. Right, this last distance is 0.88. Here was 0.48. So that means that the Y0 for this case was 0.4 meters. Let's go ahead and check that out using the second equation that I looked at. It said that the amount of stretch that I would expect if I hung a 250 grams, so that's 0.25 kilograms, 9.8 for little g. And then I'm going to use the same spring constant I just calculated on the first page. I didn't change the spring. So I just put that there, and lo and behold, if I put that in the calculator, I get 0.4 meters. So that's kind of consistent with what the simulation predicted here, what would happen. All right, so this resting position that we just found here in this middle picture, we're going to call this the equilibrium position. And now what I'm going to do is I'm going to grab this mass and I'm going to pull down on it. I'm going to stretch it a little bit more. The amount that I'm going to stretch it, I'm denoting by this purple letter Y with a prime next to it. So I'm going to stretch it down even further. And once it's down here, what I'm going to do is I'm going to release it. Now what we're going to do now, once you're down here, the spring force is bigger than the weight. So it's going to start moving upward, okay? And eventually it's going to go up to some maximum height, and it's going to start to oscillate up and down. The mass is simply going to move up and down. My goal is to just examine what happens over here. What if I stretch it, for example, 10 centimeters or 12 centimeters? How high does it go after? Okay, so that's going to be the goal of the next experiment here we're going to do with the PhET simulation. All right, so here's the simulation. Again, the equilibrium position is this green line here. It's at the 64 centimeter mark. And the initial unstretched spring is approximately 48 centimeters, close enough. Still wiggling up and down a little bit, but that's okay. It's because it's not exactly at 64 when I set it there. Now my goal here is to move it to 90. All right, so I'm going to add a line here. And we're going to move it right. Oh, I can't move the ruler, silly. I will move the line, and the line I want to move it, put it right at 90, okay? So if I do that now, I want the center of this mass here to go right at the red line. So we'll go over here, it's approximately there, and now I'm going to release the mass, and let's have a look at what happens. All right, now it's going way too fast, so we're going to slow it down a little bit. Using the little switch down there, which is nice. All right, first thing we notice is that the mass always keeps on going back all the way to the 90. Okay, that's the initial amount of stretching that I had, right? So that's the lowest point, and it'll never go lower than that. There's no damping in this system, so the oscillations just continue over and over and over again. One thing we notice is that it goes through this equilibrium position, but it goes higher than this originally unstretched spring, right? Look at where that dot goes. It goes all the way up there. So what I want to do is I want to figure out these different positions, okay? So first thing we're going to do is I'm going to try to stop it. Actually, let's just keep on moving this line and bring it all the way to the maximum. It looked like it was close to the 40. Let's go have a look. Right about there, a little bit lower maybe, right about there. Let's have a look at when it goes back to the top. All right, we're pretty close to it. Notice where this line is. This line here is at the 38 centimeter mark. Okay, we started down at the 90 and it goes all the way to the 38 centimeter mark. And again, we started at our equilibrium position, which was approximately 64 centimeters. Okay, so let me go ahead on the next page and we're going to write down all these distances to make sure that everything makes sense to us, okay? All right, so I have two situations here, two snapshots of what was going on. This was the initial release point. I said it was at 90 centimeters, and it started at the equilibrium position, right? That equilibrium was approximately 64 centimeters. But I stretched it this amount, right? I stretched it an additional 26 centimeters. That's the difference between 90 and the 64. Okay, and now I took a snapshot when the mass was kind of at its highest point. Okay, when it's at its highest point here, this was at 38 centimeters, right? 0.38 meters. However, if you have a look at now, look at this distance right here. This distance between the equilibrium position and the highest point. All right, if I do that, 0.64 minus the highest point, 38, guess what I get? I am going to get my y prime value again of 0.26 meters, right? 26 centimeters. So it's kind of like you went down 26 centimeters and then you went back up 26 centimeters. Everything is completely symmetric with respect to this line. And this line was really the new equilibrium position, right? The equilibrium position, when it's vertical, it kind of depends on the position of the mass. Okay, and that is really the key to all of these vertical problems, is all you need to do is find the new the new equilibrium position, and then everything will behave exactly the same as the horizontal system. So now we're in a position to write down an equation for the position at every single time. What we're going to do is I'm going to call this position here y equals to 0. All right, that is the equilibrium position, and what I want to do now is simply find an equation that tells me exactly where the mass is as a function of time. All right, so we're going to consider this third picture right here. This third picture, let me just label it number 3. So again, now I've started at this equilibrium position, which was y0 below the unstretched spring, and then I stretched it an additional distance y prime. Okay, and right here I'm going to release it. Once I release it, there are only two forces acting on it. There's the weight acting down, and there's going to be a spring force acting up. Now the spring force, guess what, is going to be equal to, well, it's the spring constant K multiplied by how much did I stretch the spring. Right now it's stretched a total distance y. Okay, and y is simply the combination of both of these. This is it. These are the two forces acting on it. Now the spring force is bigger than the weight, which is why it's going to shoot upwards. So let's write down Newton's second law when we're in this lowest position right here. Okay, so Newton's second law says you add up all the forces. Now for me to do that, I'm going to use this coordinate system. I'm going to define everything going down as being positive, everything going up as being negative. Okay, so Newton's second law says the mass times the acceleration in that vertical direction, okay, has to be equal to the net force. I have to add up all the forces. So there are two forces. I have the weight acting down, and I'm going to put a negative sign because this force is acting up, and it's K times Y. All right, nothing miraculous here, right? This is just adding up the forces. F net equals to MA. Now the next thing I want to do is I want to just substitute, because I know that y, just from this image here, is equal to y0 plus y prime. Okay, so let's go ahead and get rid of this guy. So we have the weight, mg, minus the spring constant, and instead of writing y, I'm just going to write y0 plus y prime. All right, now what is this acceleration in the y direction here? Okay, this acceleration in the y direction is nothing more than taking the derivative with respect to y 2 times. That's the definition of it, right? So this is really m. It's the second derivative with respect to y dt squared, okay, equals to, now let's distribute this negative sign through. So we have minus k y0, okay, what else? Minus k y prime. All right, now there's a couple important things here. Now what's a little bit tricky is you have y and here you have y prime, but we'll take care of that. But what about all of these terms? Look at this first term here. This is exactly the same expression as we obtained for this second image right here. We said that this is the definition. This is how you find y0. Right? In the first part of the video, I wrote that ky0 has to be equal to the weight. That is how you find the equilibrium position. So guess what? This term right here is actually equal to 0. So don't even worry about it. Let's just get rid of it. Now, we still have this difference between y and y prime, but the connection between y and y prime is given right here. So guess what? If I want to take the second derivative with respect to y, first of all, you don't even have to worry about this term. This here is a constant for this problem. That's the equilibrium position. So you don't even have to worry about it. If I take the second derivative of a constant, it goes away. So the second derivative of the y position is also equal to the y prime. So this is a very important step. So now at the end, what you can do is you can write one equation. So we're going to write our final equation then. It says m d2y prime dt squared is equal to minus k y prime. This is our equation of motion. And guess what? This looks like the exact same type of equation that you had for the horizontal spring and mass. So I'm just going to write that down. Same as horizontal. The only difference is for horizontal we had x here instead of y prime. But we still can use the solution that we used for the horizontal spring and mass and apply it to this problem. Remember, y prime is defined as the distance with respect to this equilibrium position. All right, we're going to go on the next page now and write down the solution for y prime. All right, so to find the solution of this, I'm just going to rewrite it a little bit differently. I'll bring the mass on the other side, divide through by the mass, minus k over m, y prime. All right, the solution to this, and something you can try, is, again, we're just going to use the exact same type of solution I use for the horizontal spring and mass. So I had an amplitude, and we had cos of omega t plus some phase angle. Now, if I release it from rest, you're going to find that this phase angle goes to 0, okay? But that's okay. Now, if you wanted to find the speed, well, the speed in the vertical direction, all you have to do then is take the first derivative of this with respect to time. So you get minus a omega sine omega t plus phi. And then you can also get the acceleration is right here, right? The acceleration with respect to time is minus, this will be omega squared, again, times y prime of t. This is the exact same treatment you do for the horizontal spring and mass. Now our omega, that's the angular frequency, is simply defined in terms of the spring properties k and the value of the mass that is connected to it. Now this is related to the frequency of oscillation, right? So you can simply write this down, that the frequency of oscillation looks exactly the same as the horizontal spring and mass system. Very important equation. Once you know the frequency of oscillation, you also automatically know the period because the frequency is defined as the period. So this is simply 1 over the period. Now, if you take this equation, you can write down, just rearrange this. If I'm just looking for the period, for example, you have to take the reciprocal of this relationship. So the 2 pi ends up swinging to the top. And then the term in the square root simply flips around. Okay, so now we know the period of oscillation. So what we're going to do now is let's go back to the PhET simulation, look at our case, and calculate what the period of oscillation is for our spring constant and the 100-gram mass that was connected to it, and see if our equations make sense. All right, so we've got a stopwatch over here, and I've got it set up at 90 centimeters. That's my initial condition. We're going to hit play here. Oh, I forgot to start the stopwatch. All right, we're going to try this again. Let's try to start at the bottom. Boom. That's time 1 oscillation. Try to stop it when it's close. Oh, close enough. 0.79. Now there is my reaction time in there. What I should do is really take more oscillations, but my experiment reveals that it's approximately 0.79 seconds. Again, this is going in slow motion right now. In reality, that's not a very long time. Okay, but let's go and do the calculation now and compare it to the 0.79. All right, so here's the equation. Again, I had 0.79 seconds from the PhET simulation. We substitute in our values. The mass that I used here was 0.1 kilograms, and the K was the spring constant. In this case, the spring constant I had, that was from the first part, 6.125. All right, put that in the calculator, and I got something that was pretty close. 0.803 seconds. Hey, not bad, considering I was just, well, it was going in slow motion, so that did help me. Let me just fix this guy. Okay, something like this. Now, if I wanted to write the equation of motion to know the position at every single time, again, the form is like this, cos of omega t plus phi. Now, again, phi for this case equals to 0 because at time 0, the object is not moving. And the velocity expression here was this guy, right? We said minus a omega sine of omega t plus phi. Well, the only way that at time equals to 0 that I can have a 0 velocity, the only way I can satisfy that is if phi equals to 0, because you substitute 0 in here. All right, let's go ahead and do it. So you do 0, you have minus a omega sine of phi, right? The first term, omega t, goes away at time 0. And the only way you can satisfy this is if this angle phi equals to 0. So, to write down the full equation of motion now for this as mass oscillating up and down with respect to that equilibrium position, again, I'm not going to need this phi factor. Again, what is the amplitude of oscillation? The amplitude was how much did I originally stretch it by? In this case, it was 0.26, and it was positive, right? So, cos, now my omega value I can find because omega is simply going to be 2 pi over that period. That's the value of omega and multiplied by time. So again, you could put everything in here. If I wanted to calculate the omega, all I would do would be 2 times pi divided by 0.803. So the omega, you go ahead and write that down, 2 pi over t. It gives me 7.82, close enough. So our final equation then, that gives me the position of that mass everywhere, 7.82 multiplied by t, and that gives me the position with respect to that equilibrium position. If you make a quick sketch of that, it would look something like this. If I plot the position as a function of time, again, you start at that lower position, and then it simply oscillates back and forth, just like a simple harmonic oscillator. The amount of time here, if you write here, this here would be 1 period, right? This time would be 0.803 seconds. That is the definition of the period, the time for one full oscillation like this. All right, I just want to say a few things about the energy now. What's the difference when it's vertical versus horizontal? Remember, the energy in a horizontal spring, for the spring potential energy, I would simply write it as 1/2 kx squared. Now it was all done. Typically for gravity, it was 0 because it was just oscillating in the horizontal direction. So there was no gravitational potential energy, or there was no change, certainly, in gravitational potential energy. How about in the vertical case? So in the vertical case, again, if I'm going to write the total, say, potential energy, again, there's going to be kinetic once it starts moving, but just in terms of potential energy, E total, say, potential. There are 2 forms, so there's going to be gravity, and then there's also spring. Okay, so how would you write those? Well, let's take y equals to 0 as this position here, okay? For gravity, everything above here is going to have positive gravitational potential energy. every point below has to have negative gravitational potential energy. So for that one, I'm just going to call it minus mg y prime, right? And y prime is the position. Okay, remember my y prime function looked like this, a cos of omega t. Okay, so you can substitute that in there. And I put the negative sign just to ensure that it's negative below that point and positive above. Now what about the spring now? The spring is stretched. Well, it's stretched by how much? It's stretched a distance y, right? It's stretched all the way from here, okay? Now let's go see what that does to this whole term. So what we're going to do is simply expand this spring potential energy. So I'm going to write it as 1/2 k, and instead of writing y again, I'm going to make that substitution for y0 and plus this y prime, but you have to square this whole term. So again, the total gravitational plus spring, I'll just call it u total, that's kind of a good one. You get minus mgy prime. Again, now plus, now we're going to expand this, okay? So you're going to get three terms. You're going to get ky0 squared, and then you're going to get plus, there's going to be 2, right? This is y0 y prime, and then the last term is just going to look like another spring potential energy, but with the y prime variable. Now the two terms that I'm really interested in here are this one and this one. Again, for the same reason that we did, if you factor out y prime, guess what? Look at this two terms, right? What you're going to get here, if I factor out y prime, is I'm going to get ky0 minus mg. Then I'm left with this, ky0 squared plus 1/2 ky prime squared. This term we've seen a couple times so far, right? That's the definition of the equilibrium position. It has to be equal to 0, so this term doesn't even exist. So at the end, the total potential energy, gravity and spring potential energy, is simply this, 1/2 ky0 squared plus 1/2 ky prime squared. Now, if you're solving energy problems, think about this term. This term here is nothing more than a constant term. So it would always be in the equation, right? So forget about it, right? This here doesn't add anything to the problem. So you don't even have to include that term really, okay? I mean, it's going to change the absolute value of the total potential energy, but it's not going to change anything else. So all we need to do then is simply include this just like a regular spring mass problem, and then we can use that now to find the speed anywhere in this simple harmonic motion problem. Okay, we treat it exactly the same as you did the horizontal spring. So let's go ahead and do one example now where I'm going to use energy to calculate the speed of this simple harmonic oscillator when it's at some position here. All right, the question is find the speed when the position is minus 0.13. All right, now we need to kind of just draw everything out here. So we're going to have the y equals to 0 position. That was the equilibrium position. Remember, my mass then started down here. I started a certain distance, 0.26 meters below. All right. Everything down here was positive. When I'm at minus 0.13, guess where I am? I'm going to be right here. The mass is eventually going to go all the way to this position, right? It's going to oscillate between 0.26 below and 0.26 above. But really, I want to know when I'm this far away, okay? Y equals to minus 0.13 meters. All right, how do I find the speed here at this position? What is V? Now, you could solve this using two methods, okay? We have an equation that gives us the position everywhere. I said you can find the speed or the velocity here simply by differentiating this, right? And that was minus omega A sine of omega t. All right, so all you need to do is figure out which time am I going to be at this position. Well, that you use the first equation. So let's first use the equation of motion approach, then we'll use an energy approach, and you'll see we're going to get the same answer. Okay, so first we've got to find the time. Well, you want to find when y prime is at minus 0.13, right? And this is my equation that tells me where I am everywhere. Okay, so bring the 0.26 on the other side. You get minus 1/2 equals to cos of omega t. I can solve this for the time. All right, you simply put that in a calculator. You get cos of minus 1 of minus 1/2. This here equals to omega t. I'll just leave it as omega t because eventually all I need is omega t to substitute back in here. This value right here, you can calculate this. Omega times t is going to give me something in radians. This gives me 2.094 radians. Okay, that's what that term is. So now you go ahead and you substitute that into this equation here. And we're going to get that v. Again, if I'm just worried about the absolute value, forget about that negative sign. It's going to be the omega a, then sine of this value, sine of 2.094 radians. We substitute, we had 7.82 for the angular frequency here. What else? The amplitude was 0.26. And now I do sine of 2.094. And I get a speed that's equal to approximately 1.76 meters per second. All right? That's how fast I'm moving when I'm at 13 centimeters above or even below, right? It's just depends on which direction I'm moving here. But the speed is always going to be 1.76 meters per second. Okay, that's kind of using this equation of motion approach. First finding the time and then substituting into the velocity equation. Okay, that's pretty straightforward. Now, how would I solve the exact same problem now using an energy approach? So, how do we do energy approach for this type of problem? So let's go ahead and think about it now. I said that the potential energy, the total, right? The total potential energy, which includes gravity and spring, you can write it like this as a constant plus 1/2 ky prime squared. That's it. Okay. So what we're going to do is I'm going to compare what is the total energy at this position and equal to the total energy at this position. Right? This is my initial configuration and this is my final. Okay? For me to take care of everything, this is all I have to do. You don't have to add additional gravity in here. We already done that when we derived this equation. So this is what it looks like. So I'm going to compare initial to my final. So initial, what do I have? Well, I'm going to have u0 plus 1/2 ky prime squared. Except the y prime value is the amplitude. That's where I'm starting. Initially, I don't have any kinetic energy, so I don't even have to worry about that term. Once I'm at this position right here, guess what? I'm going to have some final kinetic energy. That's going to introduce the speed. However, I'm also stretched. I'm also a certain distance away from this equilibrium position. So I have to have this term, u0 plus 1/2 k. Now what is the y prime position here? The y prime here is minus a divided by 2. It's 13, right? I have to square that term. Started here at 26. I ended up at minus 13. All right, let's simplify some of the terms here. First of all, we get the u0s on each side. So really, you never really need to include those. They don't tell me anything. All right, the next term's now 1/2 ka squared here. I'm going to bring this to the other side. Going to be minus 1. Well, this will be fourth. This is going to be 1/2 k, and this is a squared over 4. Okay, and now I can introduce the speed here because that ends up going through this, the kinetic energy. All right, so now we have to just group some of these terms. I get, what do you get here? 1/2 ka squared and 1/2 ka squared over 4. You're going to get, let's get rid of the 1/2. So the 1/2s are everywhere, right? You don't need those. Oh, now this is easy, right? Because I get ka squared minus ka squared over 4. So now I'm left with 3/4 ka squared. And here I'm left with mv final squared like this. All right, I can bring the mass on the other side. And then I want to get V by itself, so I just end up taking the square root of both sides, and then I get V final, right? Just the magnitude that I'm looking for, the speed. And the last term, maybe you could just write this, V final. I can write this as square root of 3 over 2. Now this middle term, look at this, square root of K over M. And then I'm left with A. Hey, the square root of K over M is the definition of omega. So my V final is square root of 3 over 2. This is omega and this is A. Now you substitute in all the values. 7.82. And my amplitude was 0.26. And lo and behold, you're going to get a V final, which is equal to 1.76 meters per second. Okay, so this is a really important point about this one. Okay, that when you're going to include the total potential, right, as long as you redefine this as being, all right, the new equilibrium position is the 0, right, the only term you really need to include for the potential energy is going to be this guy. So you treat it exactly the same as the horizontal spring. There is no different, right? We've already included the gravitational potential energy everywhere in this term. Okay, so all you're doing is spring potential energy and kinetic energy, and then you can solve for the speed anywhere this mass is located. All right, hopefully that helps clarify some points about the vertical spring and highlights some of the differences and some of the similarities when you treat some of these problems.